Welcome to another edition of the Finite Element Seminar at Lawrence Livermore National Lab. It's our pleasure today to have Pablo Brubeck, who is a postdoc at Oxford University. He also did his PhD there with Patrick Farrell, and he's been doing a lot of interesting work on solvers, preconditioners, and other things. And today he's going to tell us about his work on FIAT, the Finite Element Automatic Tabulator, which is basis function evaluator, but also how this is then used to derive efficient finite element solvers. Pablo, the floor is yours.
Thank you very much for the invitation to speak at the seminar. So I divided my talk in three parts. First part, I'm going to introduce what FIAT is. Part two, I'm going to talk about macroelements. Part three, I'm going to talk about higher order finite elements. All of this, all of the elements that I'll be showing you in the slides are already publicly available as part of FIAT and can be used to FIAT. Okay, so what is FIAT? FIAT, it stands for the Finite Element Automatic Tabulator. So it's the part of FIAT that is responsible of tabulating finite element bases onto quadrature points or onto any point cloud that the user specifies. So FIAT, in principle, is very, very general. It can be used not only by FIAT, but any general client. And it was originally used by the Phoenix project before FIAT came out 10 years ago. So FIAT was first developed by Robert Kirby 20 years ago, and nowadays is still maintained by Robert Kirby and the rest of the FIAT team. So I'm part of the FIAT team, and I am very much involved in the development and maintenance of the FIAT package. So the aim for today, I'm going to show you how we implement a lot of very interesting finite elements and how these elements have very desirable properties and how you can use them very easily through FIAT. In particular, macroelements and specialized high order bases to in the end get you produce very efficient finite element solvers. So how does FIAT work? Okay, so FIAT uses the mathematical definition of the finite element given by Hsieh-Clough-Tocher. So this is a very classical definition. So a finite element is a triple where we have K, that is the domain of the finite element. So one finite element is defined in one cell, and this cell could be the reference cell or could be any other cell in a mesh. The second thing in the triple is P. P is the local function space. So this could be a space of polynomials of, let's say, vector value polynomials, tensor value polynomials. It could be polynomials that include total degree less than or equal to a given number, or polynomials or trimmed polynomial spaces, such as the Raviart-Thomas space. So FIAT mostly works with polynomials, but nothing stops us from implementing finite elements defined with functions that are not polynomials. And the third thing in the triple is L, which is a set of functionals. So this is, it should include a basis of functionals that span the dual space P star. So let's look closely at the third object, L. So these functionals are nothing more than the degrees of freedom of the finite element. And we want these degrees of freedom to have some association to the entities of the cell. So the vertices, the faces, the edges, so that we can glue them together to get the right continuity of the finite elements that we design. So if we want H1 conformity, we need to have function values that are continuous on vertices, edges, faces, and also values on interiors. So let me give you some examples of functionals that we support in FIAT. We have evaluation at points to give you Lagrange elements. We also have derivative at points to give you C1 conforming finite elements. And we also have support for integral moments to obtain other basis functions that are, for example, hierarchical. And we have many others, higher order derivatives or moments of vector functions, so moments of one component, you name it. These degrees of freedom are very useful to get desirable properties such as sparsity, as we will see in the last part of my talk. Okay, so how do we construct finite elements with this definition? So from that definition, there was something very essential to the finite element that was missing, and that's the basis functions of the finite element. So traditionally, codes that for finite elements would explicitly code the basis functions. An alternative to that is what we do in FIAT. So in FIAT, we never prescribe basis functions. We only prescribe degrees of freedom. An advantage of that is that we can interpolate onto the function space very easily by simply evaluating the degrees of freedom that we know. So in order to get the basis functions, we do the following. We construct a set of primal basis functions from the set of degrees of freedom, satisfying that the degree of freedom I evaluated with basis function J gives Kronecker delta. So we're going to write down our basis functions as a linear combination of another known basis for the polynomial space P. So this could be, for example, the orthonormal polynomials on a simplex, or if you're familiar with the do-binary polynomials. And this is what we use most of the time. So it doesn't really matter what's this set with the Q. In the end, we arrive to the primal basis by solving the following problem. So from the Kronecker property, the fact that we want our basis functions where we have only one of them evaluating to 1 for a given degree of freedom. If we apply this equation onto the expansion in terms of the known set Q, we obtain a linear system of n equations and n unknowns, and we basically solve a matrix system of equations where the right-hand side is the identity. So the matrix of expansion coefficients is simply the inverse of B transpose, where B transpose we denote as the generalized van der Monde matrix. So it's evaluating the known basis with the degrees of freedom. You construct this van der Monde matrix for the set of degrees of freedom that you have, and then you take the inverse transpose, and that's the right coefficients in the linear combination for the primal basis function. That's how we construct lots of elements that are defined with the classical Hsieh-Clough definition. Okay, so once I stated that, let's move on and see the recent features that we added regarding macroelements. So here are some macroelements. Through this talk, I'm going to be showing lots of pictures like this. So these are finite element diagrams where the degrees of freedom are denoted with glyphs. So on the left, you can see the red triangle that has a few dots denoting degrees of freedom as point evaluations at those vertices. So here, this macroelement is basically splitting the cell into 4 smaller subcells, and on each subcells, we're gonna be a linear function, a piecewise linear function, C0 continuous, and we're gonna have the degrees of freedom that a quadratic would have on the larger cell. So this element here is a linear element, but it has the degrees of freedom of a quadratic element. We call it P1 iso P2. On the right, we have another macroelement where the cell has been split by taking the barycenter and then connecting it to the 3 vertices of the triangle. We call this way of splitting the cell, splitting the triangle, is also known as an alpha split. And here again we have piecewise polynomials, this time quadratic, and here you can see the degrees of freedom on each subcell. And we even have more exotic macroelements. Here I'm showing macroelements that are C1. So these functions glued together with their function values denoted by circles. By function values are denoted by points, and the circles around them denote the gradient. So these functions glued together, not only having continuous value, but also continuous gradient, and these are useful to solve biharmonic problems. These other degrees of freedom on the edges are denoting normal derivatives along on the edge midpoint. And here, as you can see, this element is also a macroelement splitting with the alpha splitting. We also have a reduced version of this element where the normal derivatives are not there. HCP stands for the 3 people that work on this element, the Hsieh-Clough-Tocher. And there is also the reduced version of that. And here on the right, I'm showing an element for stresses in solid mechanics. So this element is known as the Johnson-Mercier macroelement. And it discretizes tensors. And for each tensor, we have degrees of freedom on faces that take, so for each tensor, you have two indices, right? So the thicker arrow denotes the normal, and normal tangential components of the symmetric tensor. And that's how this finite element glues together. The normal component of this function is continuous. So both normal tangential. And there are some interior degrees of freedom for each independent component of the symmetric tensor. So 3 on the interior in 2 dimensions. Okay. So why did I talk about the CR definition earlier, just because using this mathematical definition to define our non-macroelements turned out to be very effective for us to implement macroelements. So we didn't have to change much of our code just to include macroelements. We had to work on top of the CR definition and just allowing more just allowing more general cells instead of just working with simplices. Now we're allowing splits of simplices. So these are mathematically described as simplicial complexes, where you can allow cells with more than one entity in the highest dimension. So the alpha split has 3 triangles as cell interiors, and the same number of spaces and same number of vertices as the triangle. So here the simplicial complex for this triangle includes 3 cell interiors, 3 edges, and 3 vertices. And we also have to specify how these are connected. Sorry, there's also a 4th vertex. There's the interior vertex that we added. We had to change the way we dealt with function spaces. We had to allow piecewise polynomial spaces now on these simplicial complexes. And we construct them with certain continuity. For example, we want them to be C0 continuous or C1 continuous, or we just want to have continuity of the normal components, for example. And lastly, we had to change the way we specify degrees of freedom, because now we can specify them on either the entities of the split cell or the entities of the unsplit parent cell. 4th ingredient that we need to consider was how are we gonna be integrating on this split simplices. So we needed to incorporate composite quadrature rules, and these are very, very easy to construct. We just take a non-split quadrature rule, and we just tile the split cell with it by applying mappings. So why did we pursue macroelements? So macroelements are a very active area of research in finite elements. There's lots of exciting stuff happening all the time since the very early days of the finite element. And the finite element, one of the main motivations was its simplicity and how you could obtain solutions to complicated problems with very simple basis functions. So the spirit of the finite element traditionally has been to pursue the lowest order possible. So here's some examples for different function spaces. I'm going to show you what was the lowest degree that you could get with macroelements and non-macroelements. So if you're solving Stokes, the first space, if you're solving mixed elasticity, where you want symmetric tensors that are H-state conforming, the lowest degree you could get with macroelements is 1, and the lowest conforming non-macroelement is the Arnold interelement and has degree 3. And if you're solving Stokes and you want H1 conforming divergence-free vector fields, the lowest degree that you get with full polynomials on an alpha split is 2. If you don't have macroelements, there are mesh restrictions, but on a general mesh, the lowest degree that you go with full polynomials is 4. If you're solving the biharmonic problem, With macroelements, you can use cubics. Without macroelements, you have to use the Argyris element, which is quintic, if you want full polynomials. You're solving Stokes, Navier-Stokes in 3D. With macroelements, you could use cubics. With non-macroelements, you get, with full polynomials, the lowest order would be 6. Okay, but what if I'm not interested in low order? I like high order personally. Why should I care? Okay, well, high order is hard. You need very good solvers, and a key ingredient of the solver is very often a low order core space. So with macroelements, you could arrive to lower order core spaces. And another way of solving high order problems is by constructing macroelements that are linear, or but have the same degrees of freedom as the higher order elements. And this is done in FEM, and I think it's really great. These are the equivalent low order refined preconditioners for high order. And we also like macroelements because they let us avoid extra inter-element continuity, which is also known as super smoothness. So this greatly facilitates the implementation of solvers or discretizations for the biharmonic and mixed elasticity, especially in 3D. Okay, just to elaborate more on super smoothness, these are some non-macroelements, as you could see, as I'm not splitting the cells. We have the Bell macroelement for the biharmonic, the Argyris element for the biharmonic, and the Arnold Winter element for mixed elasticity. And as you can see, here we have not only function evaluations, first derivatives, but also second derivatives. If we want to see one function, we should prefer a method that does not require continuity of second derivatives. We only need continuity of first derivatives. And macroelements offer a way of just imposing the right number of derivatives, giving us a much cheaper discretization. Here in the linear elasticity case for the tensors, the non-macroelement requires the function to be continuous at vertices, but the natural continuity requirements are just on faces, and with macroelements we can achieve this. So we get some in the end, the macroelement would be easier to implement if we had the machinery to support piecewise polynomials on a split cell. Okay, so let me show you more macroelements, and this is these are two other ways of splitting a cell. So here I'm splitting the triangle in 6 little triangles, and here I split it with 12 little triangles, and these two elements can be used to solve the biharmonic, as well as these other 3 elements that you already seen. And here I'm showing the HCT triangle, which is cubic, but we also support high order variants of this element. So here you can see the degrees of freedom for the degree 4 HCT triangle. And we also have HCT for general degree. And now I'm going to show you how simply you could use them to solve the biharmonic with FIAT. So in one slide, here's a self-contained code that solves the biharmonic. So here we create a mesh. We define our finite element space by just passing the name of the finite element family. In this case, I'm using the reduced HCT, which is simply HCT-red. I need to say it's cubic. And then I define a variational problem with the usual syntax. So here I'm solving biharmonic, saying that the gradient of the gradient of u tested against the gradient of the gradient of a test function should be equal to the right-hand side, 1 in this case, the test function. I prescribe boundary conditions everywhere. And here I solve the problem using PET-C options. In this case, I'm showing here how these elements combine with all the features that FIAT has in terms of solvers. And with this simple code, I'm obtaining a 6-digit residual reduction in 10 V cycles. Another example, we could try this. Let's say we want to solve Stokes with macroelements. So we could take a familiar space like CG. Let's say we want the lowest order Stokes element, which we obtain with quadratic CG on an alpha split. And we can do this very easily by just passing a variant. Here variant could be either how you want to choose the points for CG. If you want equispace points, non-equispace points. I'm gonna touch on that later on. But here I'm using variant. I'm passing alpha to get the macro element on the alpha split. For the pressure space, I need DG1 on the alpha split. And then I simply define the variational problem of the Stokes flow in the usual way, specifying boundary conditions and solving. This formulation gives me a point-wise divergence-free solution. And here I'm computing the norm of the velocity, and it's effectively 0 to machine precision. So if the variant alpha weren't there, the method would not be inf-sup stable, the problem would not be solvable. We would have to use degree 4 on this mesh. Okay, so we mentioned Stokes, we mentioned inf-sup stability. The construction of inf-sup stable finite elements for Stokes that are conforming, divergence-free, but also low order, has been one of the greatest challenge in the field. And there's lots of work out there, lots of different methods. Very few of them check all the boxes. And here I'm just showing a sample of these methods, very important ones. So one way of getting a pointwise divergence-free solution is using H-div elements, but those aren't H1 conforming, so you have to use interior penalty methods. And that's the price you pay if you want to achieve a very low order. Here I'm denoting the degree here of the Raviart-Thomas with this interval, because the Raviart-Thomas elements do not include all linear functions, just some of them. So they include all constants, that's why I put the 0 there, but not all linears. There are other elements that include all linears and some d-degree bubbles, which are called the Bernardi-Rauge bubbles. These are conforming inf-sup stable, but they are not degree because they are of higher degree and the pressure is constant for them. So you cannot enforce the divergence of the high degree functions to be exactly 0, only weakly. So this fails to be dict-free. Taylor-Hood elements also fails to be dict-free. It is conforming, inf-sup stable, but not divergence-free. I was talking about the full polynomials in earlier slides. So these are attributed to Scott and Bokili. That's why I put SB in their name. If you choose for d dimensions, the degree 2d, 2 times d, then you get conforming, inf-sup stable, and dict-free. But the degree might be too high. We might be happier if we can go lower, and we can do this with macroelements. But can we do even lower? Can we get something like Bernard-Hirault? Can we do all the linears plus some other high degree functions? Okay, yes, we can. So macroelements allow us to achieve lower order, as I mentioned before, and we can obtain the lower order by constructing the elements with the Stokes complex. So this is a way of getting elements for the velocity with finite elements for string functions. And in 2D, the string function can be discretized with C1 elements. So on this diagram here, I have the string function element. If I can construct the velocity as a curl of the string function, but I also need more functions to make this space complete. So on the last part of the diagram, we have the pressure space. And we basically construct velocity spaces by taking a curl of the string function element plus some kind of inverse for this divergence, which we obtain by multiplying x times the pressure space. And this is how you construct this element where you almost have the degrees of freedom for quadratics, except that on the edge, you're missing the tangential component. You only have the normal component. There are other ways to obtain Stokes discretizations. In this other case, we could ask for continuous pressures on a split cell that, denoted by Kr. And here I'm showing a different type of cliff to denote that our degrees of freedom on the vertex of the triangle also include the value of the divergence and the value of each vector component of the velocity. So this element could give you a continuous pressure like Taylor-Hood, but would also get you an element that is conforming, inf-sup stable, and divergence-free, whereas Taylor-Hood will fail to be divergence-free. So this is very cool. What about 3D? The picture is more complicated because the string function is a bit more mysterious. So the string function element would not be a scalar, it would be a vector. And that the picture here would start from a C1 element, and then it would take you to the string function space. And if you take the curl of the string function, you get a velocity, and the velocity is paired with the pressure. The divergence of this velocity space should match the pressure space. We don't know how to construct it. There are ways to construct it, but these are very complicated. So an alternative to this was given by Guzmán and Neilan. So they constructed macroelements in any dimension by taking a simple space like piecewise linears, and then just adding extra functions that are divergence-free. These functions are of high order, so these are phase bubbles. So that means that they are of degree d in the dimensions. So quadratics in 2D or cubics in 3D, and they are macro functions, so they are defined on the split of the cell, on the alpha split. And they present a bunch of different discretizations for Stokes, but the most important ones from their work is the one that I just mentioned. Just take piecewise linears and add the bubbles, or just take the three-dimensional analog of the alpha Sorkin element, which is quadratic, with the quadratic degrees of freedom on the tetrahedron, with divergence at vertices. But you need to add these phase bubbles to get inf-sup stable pair. As I mentioned, we have the Johnson-Mercier available in 2D and 3D, and we can also solve problems very quickly with this element by just doing the same thing. Just define the function space by just referring to the element. This can be, the abbreviations are quite straightforward, but they are available in the documentation. And just because I'm running out of time, I'm just gonna quickly show you the pictures that we obtained with this element here. The nice thing, the nice feature about this example is that we are combining a macro element with a non-macro element in a simulation. So FireDrake can easily do that because all elements are just created equal. They're CR-led triples, and they combine very nicely with all the features in FireDrake. So the pictures that I just showed you are very pretty, but if you want to implement these things, it's not going to be very pretty. It's actually very hard, and the hardest thing is how you map them from a reference element to a physical cell on the mesh. And this is going to happen because all of the elements that I show you for the biharmonic and for Stokes and for linear elasticity have degrees of freedom that involve normal tangential components or derivatives. And these degrees of freedom do not play very nice with affine transformations. So you have to, if you want to map them, you have to recombine the reference basis functions to obtain the physical basis functions. This is, in my opinion, is often overlooked, and we are not giving the proper attention to it when it comes to the literature. And it is actually very interesting as well. But I cannot spend much time on this because I need to move on to the next section. But just to recap the first section, we support macroelements. Those give you cheaper discretizations for the biharmonic, Stokes, and elasticity. And if you love low order, you will love macroelements. If you love high order, I hope that you will also love macroelements like me. So now we're jumping to high order, the work that I've also done for high order. So the nice thing about high order methods is that they converge very rapidly, and they are better suited to use modern computer architectures because of all the data locality in these computations. They expose structure for fast operator application like matrix-free, sum-factorized codes. And they also expose structure for solvers. And one of the approaches that works very well in terms of product cells is the fast diagonalization methods. It's not very clear how would it be extended to simplices. And here I'm going to show you briefly what we've done as a first step to extend the method to simplices. And why simplices? Well, we want to describe complicated geometries like this ones. And we also like simplices because they offer mesh adaptivity. So adaptive mesh refinement is one of the features that is easily achievable with simplicial meshes. I'm just gonna skip some slides because I'm running low on time. So briefly describing how would you solve, let's say, the Poisson equation with high order elements. So you wouldn't want to assemble the matrix. Instead, you could consider a domain decomposition approach where the subdomains are constructed around a vertex. You basically take all the degrees of freedom of the cells, the edges, and the vertex itself on this vicinity that we denote the vertex star, the vicinity of the vertex. And you do this for every vertex of the mesh, including this one here, which is not shown, but you would have overlapping subdomains. And you solve a small problem on each of these subdomains. You add the solutions together, but you also solve the problem for the low order rediscretization of the PDE. And then you iterate. And it can be shown that the number of iterations required to solve the problem should not grow with the degree, the polynomial degree. And this is very cool. But there is a problem. The subdomains, as P is increased, are going to be difficult to solve. In 3 dimensions, the vertex star subdomain would, like on a regular mesh, would typically have 24 tetrahedra. That's quite a large number of just cells on this very simple subdomain. So then, as P is increased, as the polynomial degree is increased, the cost of this problem is going to be prohibitively expensive. So how do we solve these problems? They cost P to the 7 operations to assemble. To factorize them cost this P to the 9. And just to apply it each time and each iteration, that's P to the 6. It's very expensive. So our approach is to define new finite elements that give much sparser matrices. And this is for some problems like Poisson. So to be more concrete, here we're dealing with not just Poisson, but also the Riesz maps of the RAM complex. So these problems have 2 terms. There's a mass term and the stiffness term. And the stiffness term could have gradient against gradient, like in Poisson, or the curl against curl. That's for electromagnetic problems, or the divergence against the divergence, or porous media flows. And we want to do this, as I said, in triangular and tetrahedral meshes with very high degree. So this is a picture of how the stiffness part of the problem would look like in the new finite element bases that we propose. So for the Poisson problem, we have the Lagrange elements. This is a picture for degree 10 on one element. This is just one element. And here we construct the basis with special orthogonality properties that does not couple the interior degrees of freedom that are numbered last with the facet degrees of freedom. So vertex, edge, 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 6 edges, 4 faces, and you can see they're not coupled. They're not coupled, and we extended this idea in a very cool way to the curve problem and the Raviart-Thomas element for the H-tip problem. So these two are degree 10, and I don't know if you can see here, but like the coupling for the face degrees of freedom of the Raviart-Thomas is very sparse. There's only a 4x4 array of non-zeros here. Okay, let's see some examples for these 3 problems. I'm gonna use the same solver structure, which is conjugate gradients with the domain decomposition method, where on the subdomains, I'm not including the interior degrees of freedom. So these have been removed from the subdomain problems, and I just do something very cheap there. I'm just doing point Jacobi for the interior. And for the skeleton of the mesh, I build my vertex patches with only the edges, faces, and vertices. And then I solve those problems with Koleski factorization. And I also need a core space, so I'm just gonna solve that directly, but I could use a multigrid method there as well. Geometric multigrid, algebraic multigrid, anything. So this is my own slide with numerical results. So here I'm solving 3 problems, so 3 columns, 3 problems with different polynomial degrees. I'm showing the number of CG iterations required to reduce the residual by 8 digits. And here I have 3 colors. It's color coded. So for the Poisson problem, I'm using vertex patches and the lowest order. And as you can see, number of iterations with this new basis does not grow with P. Remember that here I'm decoupling the interior from the skeleton of the mesh. So the problems that I have to solve for each subdomain do not include the interior. And for the interior, I just do Jacobi. For the H-curve problem, for the curve problem, I'm doing different type of subdomains. I build my subdomains around edges. And I also need to build an auxiliary problem with the gradient of H1 functions. So CG functions, I take the gradients, and then I build vertex patches for the Poisson auxiliary problem. And then I combine this with the lowest order H-curl element. And I also see robustness with respect to the polynomial degree. In 2 dimensions, the H-tip problem is exactly the same as the H-curve problem. It's just a rotation. So I should see the same results if I use the same solvers. In 3 dimensions, I could forget about the auxiliary problem and just solve H patches for the H-tip problem, and I get very nice iteration counts. Well, let's talk about this exciting new finite elements. How would you define them? So let's start with 1 dimension. Here I'm showing you the finite element diagram for a 1D Lagrange element. The degrees of freedom are just pointwise evaluations. We want to choose new degrees of freedom to have bases that are orthogonal on this cell. We want the orthogonality to be in both the mass term and the stiffness term. So we define the new finite element. We want functions to be continuous, so we have no choice other than prescribing point evaluations at the vertices, but there's some freedom on what we can do on the interior. For the interior, we're gonna construct a basis from the fast diagonalization method. And this is to find polynomials that vanish at the polynomials Si that vanish at the boundaries that have derivative that is orthogonal, and the polynomials themselves are orthonormal. And we define our degrees of freedom to be integral moments against these eigenfunctions. And this is how they look like. So on the top, you have the standard Lagrange basis, which gives you dense stiffness and mass. On the bottom, you have this new FEM base functions for the interval, where you obtain a diagonal stiffness and very sparse mass matrix. But you might wonder, there are other bases, like the hierarchical bases, that also give you sparsity, very sparse stiffness and mass. But the problem with this basis is that we could do much better in the math matrix, and the math matrix is going to become very crucial, because in higher dimensions, you take tensor products of the mass matrix against the stiffness matrix to get the Laplacian, as I'm showing here. So if you are on a tensor product cell, you can just form the stiffness matrix if your element is essentially a box. This doesn't work if you don't have a right angle box. But in that case, as you can see in 3 dimensions, you have to take tensor products of the mass matrix in each direction, except for one direction, where you put the stiffness matrix there and add everything together, and you get products of 2 mass matrices. This mass matrix better be as sparse as possible. So this is why we advocate for our choice of basis. So if you are doing things with the standard basis, you get dense blocks. If you use the FTM basis, you get a diagonal interior block. Not only that, but the Koleski factor is also very sparse. That's great, but I was advertising that we can do something for simplices. So for simplices, we do something very similar, and we do it in such a way that it applies to H grad, H curl, and H tip, or CG, Nedelec elements, and Raviart-Thomas, or for Nedelec second kind or VDM. So we define degrees of freedom as interior moments against the similarly constructed polynomial basis to get sparsity in the mass term and in the stiffness term. So to describe how these degrees of freedom are defined, we have a very similar story as in 1 dimension. We need continuity at the vertices, so there's no other choice than point evaluations at the vertices. And then for the rest, for every subentity, that is, for every edge of the simplex, for all faces and on the interior, we choose interior moments of the gradient of some polynomial, very carefully chosen, against the gradient of the input. And we are integrating on the surface, and here the S denotes the surface gradient. How we choose this basis of polynomials? So we want this to be bubbles, so we're choosing polynomials that vanish on the surface, on the boundary of the sub-entity S, such that their gradient is orthonormal and the functions themselves are orthogonal. And that is what gives us the sparsity. And here the nice thing is that we only compute this once for the reference cell. We don't have to solve a bunch of eigenvalue problems. And just as a reference, here we have the hierarchical basis of Boitler and Trouble. And this is the sparsity that we get on a triangle for the stiffness matrix A. As you can see, the stiffness matrix does not have coupling, but there's a but. The mass matrix would have quite a lot of coupling. So this will work very well for a problem that is stiffness dominated, which is the difficult case. In 3D, the hierarchical basis would have a lot more coupling, a lot of more interesting things going on. Our basis, our construction would decouple the interior from the interface, and it would entirely decouple the interior functions. But again, the mass matrix would have the coupling. This is a vertex. This is the Koleski factorization of one of the vertex patch problems, just one. And this has 24 cells. If you do the standard thing with Lagrange elements and include the interiors, you get close to 100,000 non-zeros. But even for degree, I think this is degree 10. Even for degree 10, most of the degrees of freedom are on the edges and the faces. You reduce the number of unknowns. If you remove the interior, you reduce the number of unknowns from 1,000 to 600, and the number of non-zeros for this matrix would be reduced by 65%. But yeah, one would expect that a higher degree, this would bring significant gains. Okay, I'm running out of time, but I can show you how we construct H-curl elements and H-div elements in a very similar way. So we have degrees of freedom on edges that are interior moments against polynomials. You don't have to do anything super fancy here. The important bit is what you do on faces and on the interior. You would choose two different kinds of degrees of freedom, and this is using a construction given by Leszek, Denkowicz, and co-authors for degrees of freedom for interpolation. Here we're using those degrees of freedom to construct a finite element. So we choose polynomials, the same polynomials that we choose for the H-graph problem. We take the gradient and we define moments against that on each face and each interior. And now we pick new polynomials and we define curl moments as our degrees of freedom. These new polynomials are very special. They're constructed in such a way that the curl is a basis for the curl of the bubbles It's a bit too complicated, but bear with me. And they're constructed in a very similar way as the functions in 1D, except that now instead of making derivatives orthonormal, we're making the curl of these things orthonormal. For HDiv, it's the same story. You just replace grad with curl and curl with div. And this brings me to this last picture, where you can see the sparsity pattern that we obtain for H curl is much better than the sparsity pattern we obtain for H1 for the Poisson problem. Again, there's no coupling between interior and interface. That's very good, but the mass matrix has it. And we expect that this solver would degrade if the mass matrix is dominating. To wrap up, I talked about FIAT, that offers a very general framework to construct finite elements. This allows us to implement macroelements to solve the biharmonic, Stokes, and mixed formulation of elasticity at the lowest degree. And we also talked about high-order sparsity promoting bases that give a cheaper alternative to static condensation in our high-order solvers. And that's it. Thank you very much.
So in FIAT, you mentioned that you have this perspective of starting from the degrees of freedom and implying the basis. How does something like the Bernstein basis fits into that, where it's more natural to start with the basis?
Right. So FIAT does have Bernstein elements for simplices, but you're right. It's more natural to talk about the basis functions themselves there. So FIAT would not do the usual thing that it would do for anything else. We also allow mechanisms to just plug in basis functions and define finite elements like that. But we want to give you the ability to interpolate onto the finite element space.
But you could interpolate in a different basis and change basis or something like that.
We could project as well.
Like auto projection. Okay. I just wanted to point this out, that it's not always there are cases where you want to start with the basis. So FIAT and in general FireDrake, is this mostly Python or can it also be called from C++? What's the kind of language environment?
Okay, so the user would write Python scripts like the ones I show on my slides. Mm-hmm. But under the hood, the FireDrake converts the Python input. So the specification of variation form would be used to generate code that would be compiled in C to run very efficiently.
I guess my question was like, if we want to use, we want to couple with FIAT and FEM, is that straightforward? Is that, or will it only work with PyM?
So if you want to have access to the tabulated bases that we can prepare, I think it would be tricky if you want to call them from C, but there's always a way, I think. And the nice thing is that this should only happen once when you compile your code. So it should be a compilation step that calls Python and save the tabulation onto a file and just paste it into the code that you generate.
Yeah, okay, I see, yeah. Will has a question. Will, do you want to unmute and ask it?
Nice talk, Pablo. Really enjoyed it. My question is, if the basis function evaluation is going to be the p to the 6 complexity, or does FIAT also enable some kind of sum factorization, Bernstein-Bezier algorithms?
So the computation of the basis would be driven through the Hsieh-Clough definition. And as I showed in my first slides, that involves solving the Vandermonde system, which is gonna basically, we expect that matrix would be p cubed by p cubed, and you need to factor it. So computation of the basis would be p to the 9.
And yeah, that's done offline, right? That's done offline, but then
that's an offline cost. Yeah.
And then, but you might need to use the action of, say, the
evaluation
you solve.
Right. So the action, if you save it into a file, it would take you p to the 6. Yeah.
All right, thanks.
I'm just curious if you have it's very interesting, everything you do for how the simplices for us. That's something that we're also very interested in. And I'm just curious if you have some comparison, I don't know, for the same mesh size or same type of problem, what's the relative performance between how the simplices and how the hexes, how the tets and how the
that's a good point. I would
hexes.
expect
How much cheaper the hexes are, or how much more expensive the tets are.
Yeah. So I think we're far away from in terms of the orders of magnitude. The simplex hex solvers would be p to the 4, where here I think we are at p to the 6, but it would be very good to measure that in actual time, actual runtime, which I'm still working on the manuscript, and I think that's a very good thing to include. Yeah.
It's not just the complexity. I think you probably will get more iterations. The solvers probably are not as close. I don't know, but that's my guess.
Yeah.
I think that's an interesting thing to compare, because yeah, it's nice to know how big the gap is when we're trying to get people excited about simplices. Of course, they're excited from the meshing part, but not from the performance part.
Yeah.